All right, we're going to talk now about confidence intervals, and we're going to begin by thinking about confidence intervals not in an asymptotic regime, but what confidence intervals are, how confidence intervals are constructed, how they engage with sampling distributions, and then later in future lectures, we're going to think about confidence intervals in asymptotic statistics. When we think about confidence intervals, often there's this idea of pivoting that we need to engage with, thinking about the sampling distribution of the sample mean and how far we might find it from the population mean, and moving to thinking about how far we might find the population mean from the sample mean. And while those two sound identical and are identical, thinking about things in one way versus the other will have implications when we're engaging with confidence intervals. So we're going to begin by discussing confidence intervals and pivoting, and then we're going to think about developing a confidence interval when we have a Gaussian distribution with unknown mean but known variance. And that will help motivate a lot of things when we engage with confidence intervals in asymptotic scenarios. All right, let's return to one of our favorite scenarios. We have n observations drawn independently and identically from some distribution f that's unknown. And we've talked a lot now about estimating mu, the population mean of that distribution. And we know that the sample mean is a good estimate of that population mean. However, that just gives us a single number, sort of our best guess for that population mean. We might want, rather than a single number, a range of values that we're pretty confident that that population mean is in. And generally, if we have a large sample size, that range will be narrower, versus if we have a small sample size, that range might be wider. And so this range will take into account the uncertainty that we have when we say give our single point sample mean estimate. So we're going to talk about this as an interval estimate. This interval estimate is generally centered at the sample mean, our single number best guess, and its width is generally determined by the variability of that sample mean. So we know that as the number of observations n in the sample mean gets large, the variability of that sample mean decreases, and we're pretty sure that the true population mean should be close to that sample mean. And so what that means is for large sample sizes, we should have a tighter interval estimate, a smaller interval. And for smaller sample sizes, we should end up with a larger interval estimate because we're just not really sure where that population mean lies. One of the most common types of interval estimates used is what's called a confidence interval. This is an interval estimate with a very specific probabilistic property. It's an interval, which is going to be a function of our data, so it's random, that has some pre-specified probability beta of containing the true parameter of interest mu. So a 95% confidence interval should have a 95% probability of capturing mu. Now, mu is fixed. So what does that probabilistic statement actually mean? Well, the interval is random because the data are random. So we can still talk about the probability that this random interval contains or captures mu. So how do we form this confidence interval? This is actually a pretty subtle question. We often consider what does the relation of z bar n to mu look like? We don't often consider what is the relation of mu to z bar n look like. That second way of viewing the relationship will be extremely useful when we're thinking about confidence interval construction. I'm going to give a bit of a goofy, but I think illustrative example related to this. I live in Seattle, and so often when I'm describing where I am, I compare myself to downtown Seattle. And I might say I'm north of downtown Seattle or I'm south of downtown Seattle. Now, equivalently, I could describe where downtown Seattle is as compared to me. Downtown Seattle is north of me, or downtown Seattle is south of me. That seems a little bit strange, as downtown Seattle is in a fixed place and I am the one who is moving. However, as we'll see when we're engaging with confidence intervals, that second description will be very convenient and useful to engage with, even though in a sense it's exactly equivalent to the first description and may even feel a little bit less natural. We will see in what follows how this can help us construct a confidence interval. So we're now going to engage with a simple example for constructing a confidence interval. So for this example, let's imagine that we have these n IID observations z1 to zn, and that they're drawn from a normal with unknown mean mu, but known variance 1. Again, this is a little bit contrived. We generally don't know the variance, and it's generally not 1, but this will be illustrative and useful. So here, let's imagine we would like an interval estimate, in particular a confidence interval, for that parameter mu. Let's imagine we have, say, 50 observations. N is 50. The first thing we might do is think about the sampling distribution of the sample mean, z bar n, or z bar 50 in this case, around the true population mean mu. On the x-axis, we can see labels all relative to this unknown mu. I can't put the value of mu in there because I don't know what it is, but I do know what the shape of that sampling distribution looks like around mu, and I know what its width looks like as well. Similarly, if I increased from 50 observations to 500 observations, again, I could look at the sampling distribution of z bar 500. It's again centered at mu. I don't know what mu is, but I do know about the width of this sampling distribution and its shape around mu. And here we can see that that width is decreased from those 50 observations. So again, we might imagine an interval estimate in this case would be narrower than an interval estimate with 50 observations. Okay, let's imagine in this case, we'd like to find a 95% confidence interval for mu. So as a first step, we're going to look at the 2.5th and 97.5th quantiles of the sampling distribution. And if we consider the amount of mass between those two quantiles, we note that 95% of the mass or probability is between those two. And in this case, that 95.95 mass matches with this 95% confidence. So we're going to use that, we'll see, to identify our interval. Again, there's a little bit of subtlety in how this actually works. So let's imagine we have 50 observations. We're returning to the sampling distribution of the sample mean of those 50 observations. We have a dotted line on the left indicating the 2.5th quantile and a dotted line on the right indicating the 97.5th quantile, and the shaded region in red is the mass between those two, which in this case should be 95% of the mass of the sampling distribution. We could do something similar with 500 rather than 50 observations, and things just become narrower. For now, let's stick with 50 observations. All right, so we have this sampling distribution for 50 observations. We can now look at a single draw from this sampling distribution. So let's imagine, again, we sampled 50 observations. We looked at the sample mean. Perhaps we get the blue line. All right, we could imagine doing this again, and perhaps now we get this new blue line that's much closer to the population mean. We could imagine doing this a third time. Perhaps now we get this last blue line that is much further from the population mean. So one thing that we note here is, and this is going to feel pedantic, but I think important, if we label this width or half width as delta, 95% of the time, the sample mean will fall within delta of the true population mean. So the thing that's interesting and subtle about this is now, if we switch and we take the sample mean that we just looked at and we draw again two blue dotted lines rather than red dotted lines, now also this distance of delta from now our sample mean, z bar n, what we find is, going back for a second, if the blue line was captured within these two dotted red lines, then that's equivalent to the red solid line being captured by these two dotted blue lines. Right? And both of those are basically asking this question, is the distance between mu and z bar n greater than delta, or is it less than delta? So again, this is a little subtle, but we look at the width of the sampling distribution, we identify this sort of width such that 95% of the time the sample mean will fall within delta of mu, and then we note that if we draw an interval with that same width, 95% of the time, that interval should capture the true mean mu. Right? And so again, we can go through, and for each of these three realizations we looked at before, we can draw those intervals, and we can see for these two, The red line is captured by that blue interval. Mu is within this confidence interval we're constructing around z bar n. This final time, mu is not within that interval, right? And equivalently, this final time, the blue solid line was outside of that dotted red region. And similarly, those previous two lines where the confidence interval did capture the true mean, we see in addition that blue line is within the bounds of those dotted red lines. So, and again, this was the important key. This is sometimes called pivoting. Rather than thinking about the distance from the true mean to the sample mean, right, we can then flip things and think about the distance from the sample mean to the true mean. Right, and I think of that as like the red deltas or the blue deltas. Are we looking at the dotted red lines or are we looking at the dotted blue lines? So mathematically, when we were engaging with the red lines, we were looking at this. We were saying identify a value delta such that the probability that z bar n is between mu minus delta and mu plus delta was equal to beta, in this case 0.95, right? And this is, in a sense, directly a statement about the sampling distribution of z bar n around mu. We then noted that using that exact same delta, we could look at those dotted blue lines to form an interval around z bar n. We could look at z bar n minus delta and z bar n plus delta and say, is mu captured by that random interval? And note that if this statement held, that that probability was beta, then this statement also holds and that probability is still beta. Because these two statements are actually identical. This event is identical to this event. And in fact, both of them are asking about this. They're saying, what's the probability that the distance between z bar n and mu, or mu and z bar n, right, they're the same, is less than or equal to delta? So this idea of pivoting is critical and lets us query the sampling distribution and learn about it, identify this delta from the sampling distribution of z bar n around mu, and then from there make a statement about this interval around z bar n and whether or not it captures mu. All right, so formally again, what is this saying? Well, if we would like to form a confidence interval for the population mean, what do? We identify a value delta such that if we think about this, the sampling distribution of the sample mean around the population mean, we would like to find this value delta such that the probability that the sample mean will be within delta of the population mean should be exactly equal to our pre-specified confidence level beta. Again, we were working with 95%. Once we've identified that delta, then we form an interval that is centered around the sample mean, z bar n, and that extends to the left of that sample mean by delta and to the right also by delta. And this is what's called a symmetric beta level or level beta confidence interval. And we can see that if we think about the probability that the population mean is captured in this random interval, that should be exactly our pre-specified beta, or again, in this case, 95%. And this is called a symmetric confidence interval because the amount to which the interval extends above and below the sample mean is the same. In some scenarios, you might want to engage with asymmetric confidence intervals. We're not going to talk about that much now, and it doesn't really make a ton of sense when we're dealing with, say, normal random variables. But again, it can be useful, and these ideas can be extended for that as well. All right, let's now move back to maybe a less contrived, although still a little bit contrived example. This is going to be an important illustrative example, an important motivating example as well, moving forward when we are thinking about asymptotic confidence intervals. Let's imagine now that we have n IID draws from a normal with unknown mean mu, but now known variance sigma squared, but sigma squared doesn't actually have to be 1 anymore. And we would like, say, a 95% confidence interval for mu, and we could change this 95% to a different number if we wanted to. How would we do that? Well, again, that same recipe we talked about before. We think about the sampling distribution of z bar n, the sample mean minus mu, and we note that that's a normal distribution with mean 0 and variance sigma squared over n. And again, here sigma squared is known, so this is a known quantity we can engage with. So all we need to do is look at the 97.5th quantile of that sampling distribution. And once we identify that, again, of that mean 0 Gaussian with variance we understand, then we can form our interval by taking the sample mean and adding and subtracting that half-width, that value delta. The last piece here is that when we're thinking about the 97.5th quantile of this normal with mean 0 and variance that's not 1, we can actually relate that to the 97.5th quantile of a normal with mean 0 and variance 1, that is this piece, and then scale that up by the standard deviation, right, this piece. So this is a standard fact about normal distributions. If you want to look at quantiles of a normal distribution that's mean 0 but does not have variance 1, you can look at a normal distribution with mean 0 and variance 1, and then you can just scale it by the standard deviation of the distribution you're interested in. And in particular, this piece actually is exactly equal to, or to 2 decimal places, 1.96. And so this may look familiar, that our confidence interval's lower bound is the sample mean minus 1.96 times the standard deviation over square root of n, up to our sample mean plus 1.96 times the standard deviation over the square root of n. So again, this is a very standard looking confidence interval that you will often see. Often it won't have a true standard deviation because we don't know that. An estimated standard deviation will be plugged in instead. And this confidence interval, as we'll see later, is even asymptotically valid when our observations are not drawn from a normal distribution. So we've motivated things in this case where we imagine our observations are drawn from a normal distribution with known variance, but the form of the confidence interval is actually very, very similar to what we're going to engage with later, and we will see the central limit theorem will help us get there. So again, moving forward, we will generally not have exact Gaussian distributions and won't know the standard deviation, so we're going to have to do some asymptotic work there. We're going to have to define what an asymptotic confidence interval is, and then we're going to have to see how we can construct those, motivating how we can construct, and then we're going to have to see how we can construct those. We're going to motivate things based on what we just saw for Gaussian random variables. And we're going to see that the central limit theorem and Slutsky's theorem applied to an estimate of our standard deviation will help us basically return to the same calculation and idea.